So what I'm going to talk about here is the variable rate Poisson process of people coming in the door there. Not really, but I will be able to set you up so that you could generate that process by the end of the talk. And so the point here is that we want to be able to build realistic data. This is dry labbing 102. This is not building real data, this is building fake data. And we want to be able to build it at a performance level where we can build big enough data and realistic enough. But it's not what you might think. A lot of people might think there's going to be a lot of math here. There's going to be a little bit, not much, a lot of pictures. Pictures are cool. I'm Ted Dunning, I'm Chief Application Architect. That's why I wear the red hat. And I'm also involved a lot with Apache. This is open source that I'm talking about today. It isn't Apache. The big difference, of course, is that this is talking about a one-man show kind of project. It's a very small piece of software, hopefully very useful. Certainly, friends of mine are finding it useful. You're all welcome to contribute, but I'm not willing at this time to go to the trouble to make a real community out of this. If it goes crazy, we can do that. But right now, it's just kind of, come get it. It's open. Let's talk. Informal stuff. I also like to point out we have a number of short books that Ellen and I have written over the last year. We ran out of these. We were going to have signings and such today as well. But the first day, people took about twice as many as we expected. We brought in the spares and the reinforcements, and they took those yesterday. So, but you can still get them for free at MapR. If you go to the website and especially search for Ellen's name, Friedman, and any of the titles there, you'll find links into the books. You can get them for PDF from MapR at the cost of a registration, or you can buy them from O'Reilly or Amazon, whichever you prefer. So we also offer free, see, I've even got a pin that shows it, free Hadoop training. That's cool. Today, what I want to do is talk about, though, a very different sort of thing. The basic idea here is encapsulated in this story. We had we've got a lot of financial customers who have the risk of penetration and data diversion. The classic is the Target attack that got lots of publicity, but there's a lot of large and small attacks like this. The small ones being a restaurant which skims credit cards in addition to getting tips. It's an advanced way of getting tips, you might think about it. And they get a little bit, the crooked waiter who's doing that gets a little bit for every scan that they do. Somebody else is later going to compromise that card and attack it and do some amount of fraud. And so they can be from that scale, the small scale, to very large, where you have national state actors or very, very large criminal rings penetrating and pulling financial information with the intent to exploit it later. There may be very, very sophisticated adversaries. We may see no hint that the data is gone. We may not know that somebody's taken it. So what we want to do is, from typically the bank's point of view, find where the leak was. We don't own the organization that got compromised. We don't own their firewalls. We can't see their network traffic. We still want to find them. Furthermore, the fraud will have not been perpetrated at the original point of compromise. So it's very hard to figure out who that is. And so we want to look at our logs, our transaction logs, and figure that out. Now, the problem here, the serious, really hard problem, is that if you do machine learning, and this is kind of a general diagram of how that might be done, you have data and you have some knowledge about how things work. You use those together with a training algorithm to build a model. And then you deploy that model, that's the dashed line, into production, and you apply it to new data and hopefully get something valuable out of it, like a fraud score or something like that. That's cool. And if you've got really smart guys, you can invent new training algorithms. And if you've got really careful guys, you can tune all the knobs just right. But there's always going to be much more clever people outside your organization. So what's going to happen is, because what you're doing is inside the security perimeter, you're going to be unable to cooperate with a lot of very smart people outside, often academics, often other banks, a lot of people who have interesting expertise. You will be unable to help solve your problem. You can't give them your data. You can't let them see your data. And they may have a great algorithm, but the chances that it'll work fantastically well on your data is relatively small without tuning. Nobody can do that tuning without access to the data. And so you've got this problem. There's thousands of smart guys out there, smart folks out there. They may have good stuff, they may not. How can you find out which ones? You can't invite them all in for some sort of proof of concept. You have to find some way that they can self-select. Seems impossible. You can't move your data. You can't let them in. They can't improve the algorithm without seeing your data. It's an impasse. Well, here's one way of doing that. We can take live data, real data, the secure sort of stuff. We can run it through whatever system we're going to try to use, some kind of classifier or something like that. And out of that are going to be a bunch of KPIs, performance indicators, how fast did it run, score indicators, things like the score distributions, false positive rates, a number of things like that. They're going to get all kinds of what I call failure signatures, because typically they represent failures of the system, either soft or hard. The false positive rate is an obvious one. That's how many wrong things it's done. But the score distribution itself is a symptom of error. In an ideal system, it would give 1 and 0 for a classifier, that sort of thing. It would be a very sharp thing. The fact that it gives you a continuous range of signals is a problem. So it's a signature of how that algorithm works on your data. Now, using the techniques we'll talk about today, you can generate data. You can generate fake data and pass it through the same system. It will also generate failure signatures. It will also generate score distributions, false positive rates, speeds and feeds, and things like that. And the contention here today, the novelty here, is I claim that if you match the failure signatures, you have a random source of data that is as good as the real data for the purposes of learning how to learn. Certainly, if it produces different failure modes, it has some difference that's important. But the fact that it may not be the same distribution whatsoever, and yet could still produce that same distribution of failure indicators, and that being good enough, is not at all obvious. This is an empirical observation. But this parametric matching of that sort means that we could take the parameters of the fake data distribution, pass it to outside people. They can build their models. They can then pass us new models, and we can look at it and see if the new models still behave like on the fake data like they do on real data. If they don't, then we need to tweak the random number generator a little bit more to find something that misbehaves in just the right way, that fakes it just the right way. So the practical import is that all of these systems are scored based on how well they do, how accurate they are, what the score distribution is for positives, score distribution for negatives. And so if the random data replicates for the new system and the old system all of the KPIs and failure signatures, it by definition is good enough. Now, the exciting thing about this is that practically speaking, replicating the failure signature spectrum is much, much easier than actually replicating the distribution of the original data. The most extreme example of this that I've seen is we were trying to build with a large financial partner of ours, build a nearest neighbor model. And so it would be run in practice against transactions. So you'd have variable numbers of transactions to merchants and things like that, and we would do proximity in, is this transaction stream kind of like this user or not? We had a kind of a word count sort of proximity model. And the fake data was 10-dimensional continuous variables, just 10 floats. no transactions whatsoever. But we were able to match the false positive rates, and then with a very, very much simpler system, we were able to prototype and develop completely in open source. And this is clearly not a security leak because 10 floating point numbers have no connection to any transaction whatsoever. And so we could develop in the clear, and because it matched the KPIs, when we took it back into the secure setting, which I didn't get to see the data, the real data, it performed exactly the way it had on the fake data, as indeed it must have. And the cool thing about the random numbers in the 10-dimensional space is it had a very, very simple sort of distribution. We just did normal distribution, oh, and another normal distribution of smaller count, oh, and another one. And we picked how we degraded the sizes of those and how they were spread around the origin so that we got things that replicated the error processes. And it was really quite easy. There were about 4 knobs that we had to turn. We didn't even have to use a machine to turn them for us. We could just turn them by eye. Bam, there they are. There's the right answers. It was very easy tuning. So it was very practical. So the assertion I'm making here is that the rule that should be followed in these sorts of things is do match the failure modes and the KPIs. Do not match the exact distribution. The first is, practically speaking, very easy and good enough. The second is really hard and really starts bringing in all kinds of difficult mathematics and difficult sorts of things. And by definition, good enough is good enough. So that's what we're going to talk about today. Now, the question comes up. There's a phrase, somebody said this to me, I have no idea who said it, which is probably indicative. But they said to me, you know, actually, I'm quite famous. Most people don't know this. They were serious. They were absolutely serious there. They were convinced they were famous, even though nobody knew about it. And this sort of method of generating random numbers that I'm going to talk about here is completely widespread. It's ubiquitous, except everybody I talk to seems surprised about it. You know, but then I hear, oh, we do it too, and we do it too. So it's not like it's news, except for most people. So it's widely known, except nobody knows about it. And so this is that sort of thing. So there seems to be a lot of practical knowledge here, which just isn't very well taught, very well known. So let's start with just generating numbers. There are, of course, a lot of well-known distributions. Everybody's heard of the normal distribution, the bell-shaped curve and things like that. That is not very useful in practice because it's too idealistic. The uniform distribution is also well known, you know, uniform from 0 to 1. Every number is just as likely as any other. Poisson and gamma are less well known. Gamma is a 2-parameter distribution that can have very, very skewed distribution, or it can have kind of normal like bump distribution. It can never give you a negative number, but it gives you some very interesting positive numbers. It's really, really useful when you want something that has a certain amount of skew to it. So for instance, you might pick the standard deviation, well, the variance really, of a normal distribution according to the gamma distribution. And then you would get something that sometimes takes big steps. I'll show you that in a moment. Poisson distribution is good for picking arrival times. I put these up. I assume everybody's going to look at the slides. I'm not going to go into the details of the math. The names are good enough. And furthermore, the software I'm going to tell you about later, LogSynth, has all of these. It's really not that hard. R has all of these. MATLAB has all of these. The details are not that important from this point of view. There's also tricks that you can apply. You can transform any of these. So you might take a normal distribution and take the exponent of that, the exponential of that. So e to the normal is a positive number that has various amounts of skew, and it's kind of like a nice long-tailed description. That's a log normal thing. You can also take running sums of random variables. So if you take the running sum of a normal distribution, you get a thing that walks along like that. And if you take the exponential of that random walk, you get something that looks a lot like the growth and decay of financial systems, at least financial systems under normal circumstances. You can also do what are called mixture distributions. You can say, probably I'll pick that distribution, but I might pick that distribution. That's a great way to build long-tailed distributions. It's like a normal distribution, except when it's not. Then it might be much wider. Or you can do some very interesting things by adding up a lot of normal distributions. You can also then pick the parameters. So the normal distribution has a mean and a width called the standard deviation. You can pick those instead of as constants. You can pick those as random numbers. So here's some pictures. There's a normal distribution. Here's how you generate it in R. You generate it with even fewer characters, but still one line in logsynth. And that's what it looks like. There's a very heavy central core. Within the core, there's a lot of distribution, and the tails fall off very fast. Notice there's nothing above or below roughly 3 in this. There's a few data points that have a radius more than 3, but not many. Now, here's another thing. This is a random distribution I built just by taking a spiral and picking a distance along the spiral uniformly, and then adding a normal distribution to that. But we could, empirically, if we had crazy data like this that we observed, if we wanted to model the crazy data, we could model it as a mixture of just little symmetrical normal distributions by putting centers in these places and picking one of the centers at random. You can begin to see how you might fit a very crazy numerical distribution using techniques like this. You would just put the spots wherever you find it. The standard way of putting spots wherever there's data is called k-means clustering. So we could do a k-means clustering, and indeed I did, on the original spirally data, and I got 20 clusters there. And if I generated data by picking one of the 20 clusters at random and then just generating around that with the right, about that big distribution, I would have replicated that spiral with very high fidelity. Remember, this is, like I said, Dry Lab Class 101. This is about how to cheat. We don't have to know the internals of how that spiral actually happens. We just need to build data that looks a lot like it. This is matching the distribution, of course, but having the flexibility to do these kinds of things makes it easier to match the failure spectrum. Here's what happens when we do cumulative sums. This is a random walk. This is when we pick each step normally, the normal distribution. And they always look about like this if you rescale them so they fit the page. You could take 1,000 steps. You could take 10,000 steps like this. You could take 100,000 steps. And as long as you rescaled the x and the y-axis, you would get the same feel. They all look about the same. This is a renormalizable process. It has very nice universal properties. But if we instead pick the variance, the standard deviation, the width of the normal distribution, the step size, if we sample that again and again from a very skewed distribution, the gamma, we get a random walk. Whoops, sorry, I'm going to go out of order here. There's the other random walk that I want. You see how different it looks? This might be the sort of thing that you would see if you had a business traveler. They kind of noodle around one city and then boop, they fly to another one. And then they noodle around there, boop, they fly to another one. So this is a distribution that takes small steps, except when it takes big steps. And then it takes very large steps. This is just a catalog of tools there. Here's another one. We could take a uniform distribution, multiply it by 5, and take the floor. That gives us uniformly distributed integers, 0, 1, 2, and 3, and 4. Then I can use those integers to index into one of 5 different centers and then generate a small normal distribution. So I have this real spotty kind of distribution. Again, what we're talking about here is a catalog of techniques. You can try them on your own. Now, the next step is, I don't care about numbers. I've got people. I've got addresses, I've got zip codes, I've got transactions. They don't look like numbers. I mean, the closest some people feel like they get to numbers is when do the people arrive? Well, we can do a bunch of different techniques to generate symbols. Symbols like a merchant ID, a zip code, things like that. Well, symbols are just integers, really, and they have a dictionary. So we can pick words as the dictionary, we can pick common names as the dictionary, we can pick zip codes as the dictionary, we can pick all kinds of things as the dictionary, and then just generate integers with the properties we like. Or we can use it to look up into another table of things, and then we can get symbols that way. We can also do all the mixture games. We can do hyperparameter changing, so we can actually change the distribution along the fly. And the key thing here is that lookup tables are really cool for converting all these numbers that we had into symbols. So here's an example of a skewed integer distribution. This was generated using a standard sort of rich gets richer sort of skewed distribution. The idea is that we sample. We don't know what distribution we're going to sample from to start with. We're going to find the distribution as we sample values from it. So the distribution that we're going to sample from has a probability of picking any integer at all. It's an infinite dimensional distribution, but we don't have to find all infinite parameters. All we do is find them as we go. So we pick something that's either from the things we've sampled from so far or a new thing. There's always a probability that we're going to have a new thing. There's always a probability that our vocabulary will increase by 1. Otherwise, we sample with probability equal to the counts that we've seen, or at least proportional to the counts we've seen. And so what happens is the things we sample initially have a good chance of being sampled again, and that increases our estimate of their probability. And so you can see that 3 and 0 and 1 and 2 happen quite a lot. The first number there is the count. The second number is the integer that we actually sampled. And so what we have is a very, very skewed thing. We see short integers here much more commonly than we see long integers. This is a way, though, we can pick integers that might be foreign keys into a separate table. Now, again, the complaint is, well, I don't have these abstract things. I have people with behaviors. But we can start to put all of this together, and we can build real behaviors. We can, the real trick here is to use structured data, nested data. Don't try to build a database with behaviors in it. Try to build behavior streams one at a time. And the idea here is that we build data structures of the sort that software like Apache Drill uses very well. It's a JSON data model. We'll generate parameters for a person, like where they live. We can sample a zip code and put a little bit of fuzz around the zip code. That will give us a rough idea where the person might live. Based on where they live, we might choose what they do, because we could look up weather and use the weather as a probability generator for an activity that they do. And now we can sample, say, 365 days of what that person does. Do they go play tennis? Do they read a book? Based on historical weather from the location they're in. Or we can use the parameters we've picked for them, location, and some abstract ideas about which sort of products they buy, and we can use that to simulate purchases. That gives us then one line per person with a variable length number of transactions associated with each person. We could flatten that into a normal database, or we could just use things like Apache Drill directly on the data like that, and we can now model fraud, we can model ordinary activity. So we can put all these together. We can build honest-to-God databases. Here's a piece of the schema of a real database. We have in the center an artist, like a musical artist, and you can see we have things like dates, years, months, days. Well, you can see how to pick all those. Those are integers, right? We can see how to pick what type of artist they are. They have a separate artist table here, so we would take their table with their labels and their frequencies on those and we would pick an integer here for type that is known to be the right size to join against that table. So that's pretty easy. We can be picking things like their ID number. This is the International Performer ID, IPI number. Well, we know how many performers there are. We just pick uniformly because this is unique across all performers. Everybody has an IPI number, so we just pick a random integer. Already we've then synthesized the entire set of 4 tables on the right. Artist aliases and the artist name is a little bit trickier to generate, but we can just pick names. Again, names are just symbols. We have tables of names based on how frequent they are, how often the Census Department registers new births according to particular names. We could even pick a birth year and pick the name according to that frequency for that year. And so we can pick names very easily. We can make up some goofy way of perturbing the name to get an artist alias, and then we just have one more lookup there. So there we could build some very, very realistic data. Would it produce the right signatures of failure? Don't know yet. That's where we go with this next thing. But the key thing here, try logsynth, go grab it, and see what you can do with it. And now let's work into a real example with some real results that caught some real bad guys. So this is an example of doing model development on an airplane, completely insecurely, with no reference to to real data. I had access to realistic data that I built that exhibited the same sort of behaviors as the real problems. Here's a summary of it. The idea is we have consumers that go to merchants. They live in different places, but we don't really care where they live. We want to have a little bit of fidelity to geography based on which merchants they go to, but that's pretty easily done. And so what we want to do is generate a user, and we want to generate a rate of transactions, and then we want to generate transactions over a test period for that user. Transactions are basically at this level of detail just selecting which merchant the transaction will be. Some merchants are much more commonly transacted than others. So we're going to generate all of these users' behaviors. Now we're also going to generate another thing. Based on whether or not they go to a particular compromised merchant, merchant 0, during the compromise period, we will mark them as having been skimmed at some probability. And then during the exploit period, we pick some probability of fraud occurring on that account and some probability of fraud being detected on that account. So the life cycle of a user is I'm going to just transact. And if I transact with merchant 0 during the compromise period, I may or may not set a flag. During the exploit period, I transact, and each of the transactions has a fraud score associated with it. The fraud score will be determined by whether or not I have been compromised, I being that consumer, and whether or not that fraud is detected. You can imagine how to build this. All the little pieces that I talked about go in there. Mostly this is uniform random numbers. So for instance, we do an if merchant 0 in the compromise period, and then we pick a uniform random number, and then if that's less than some threshold, that's how we pick whether or not to take some further course. We built a little bit of code, it's about 20 lines of code, to emulate the life cycle of these fraudsters and the consumers they prey on. And here's a graph. So fraud has a false positive rate. This red line is the detection rate of fraud. There's a high false positive rate, a number of cases being detected each day. That fraud detection rate goes up when we start getting exploits from the skimming. We don't use the fact that that goes up as an important thing. During this compromise period, the number of accounts that are compromised goes up quite dramatically, up to 500 a day. There's, I think, about 1 million consumers here. And that then contributes during the exploit period to the higher rate of fraud. And so what we do is for a whole bunch of different time frames, we don't really know That we understand now, you understand, I understood before, what is actually happening. But as in real life, the model that we're testing has no idea about what's really happening. So what it does is it looks, starting at the beginning of time and for various random starting points, it looks backward in time to say, in the area of interest that it's testing, have the people been marked as fraud, have the people who have a red indicator on them, have the frauds that have been detected, do they have, what merchants have they transacted with in the past? And overall, are the counts of the people who are marked as fraud victims, are the counts of previous merchants anomalously different from the people who were not marked as fraud? There's a high false positive rate, there's a high false negative rate on the fraud detector. So we have a very, very noisy system. All we want to say is, are there any merchants in the past, before fraud was detected, who are overrepresented where fraud was detected? So that's the question. And that's the model that we're going to try to test against this fake data. And indeed, here it is. That's merchant 0, because I've ordered by merchant number here. And then I counted how many merchants had scores in different score bands. But that is merchant 0 who just popped right out of the noise. So on synthetic data, made up, totally airy-fairy fantasy, this seems to work. But later applying it to real data, we find that guy there. This is a real bank's data. These are real fraud indicators, and a real restaurant popped out way out of the noise. Look at the similarity of these distributions. There's even secondary characteristics. See that little nubbin there? See the similar nubbin right there? Those are due to integer quantization effects. You can't get every score because you can't get every different number of transactions. You can only have an integer number of transactions. You can only have an integer number of frauds. And that leads to odd quantization in the scores that you can get. And so you even replicate those odd anomalies in the score distributions. So what about these guys? This was a restaurant that was very, very close to the house of the CTO of the bank. He'd eaten there very often. He'd had drinks there. And that place had a very low rate of fraud. Did not look suspicious. When the Secret Service was asked and they checked it out, they found out that the computer systems, the point of sale terminals, had been riddled. And the reason it had a lower rate of fraud is because the fraudsters had installed anti-fraud devices to try to protect that thing and keep it from being noticed. But in fact, it was a skimming factory. And it was skimming things. So the bank here had no connection with that restaurant, except that the bank's customers patronized that restaurant and then were victims of fraud as a result. There was no serious amount of fraud at that restaurant, just like there was no serious amount of fraud at Merchant 0 in the simulation. Same model, produced the same effects. We found the bad guys, real live bad guys. So I think this is cool. I think this is fun. I'd like to hear what you guys have to say, what you think about whether or not this would be useful to you. Certainly if you're taking physics, this could be very useful because you could dry lab the experiments. But for more useful tasks, I'd like to hear. Are there any questions? Are there any comments? We have 5 minutes now. Oh, come now. Just because it's the end of the conference? Surely somebody's been thinking about this. I saw some heads nodding over there. Does this look interesting to you? Put you on the spot. Use the mic. That's right beside you.
We certainly have a complex distribution based off of our client base of production data that isn't accessible to our pre-production teams due to government regulations and whatnot. So being able to emulate that would be absolutely invaluable. And not only that, but maybe even emulating things that haven't yet happened in in
The
production
disasters that
environment.
have not happened have a certain attraction, don't they?
Right.
Detecting them in advance is really a nice thing. So you think you could use that?
I think it would have instrumental value. I just don't know how to use it. If you know.
Okay. Well, the key then is going to the distro and grabbing it. This breach emulation is in LogSynth as one of the canned demos. So you can actually modify it and try it out. So, next guy.
Hi, can you talk a bit about like heavy-tailed distributions? How they fit in?
Heavy-tailed
Yeah.
distributions. Yeah, so heavy-tailed distributions are distributions that have extreme values out of the ordinary sort of range, more than you would expect. And this random walk has a step size that is a heavy-tailed distribution. It does not look like the class of light-tailed distributions, a normal distribution. And the way you can emulate those very often is you take some scale parameter for a distribution. Standard deviation or variance is a good one for a normal distribution. And you apply to it a very, very simple heavy-tailed distribution like gamma with a small shape parameter. And so then you get these sorts of things like this.
But yeah, how do you like characterize how big the jumps will be? It's hard to get some data on that?
No, it's very, very easy because the scale of the jumps, the scale of the jump distribution is exactly the knob that you turn to make the system behave according to the KPIs realistically. You cannot easily measure the actual jump transitions because long-tail distributions are very, very hard to estimate parameters for, but you can tune it to where you find a range of distributions which give you realistic KPIs, realistic failure scenarios. So as an example of unrealistic, you remember I tuned the first example, so you see that the score for the fraudster is about 40. This is kind of a chi-squared sort of score, so that's astronomical. But the score of the real fraud was about 80. So there's clearly a difference between my simulation and the real world that I could tune better. And the way I would tune that would be just by false positive ratios, or in some cases, amount of skew. So I have skewed distribution, a heavy-tailed distribution, on which merchant is visited next.
Okay, thanks.
Yeah.
Hi, I'm with AT&T, and we get a lot of customer data. It's not necessarily financial. And as we feed in this data, I'm not necessarily interested from a testing perspective, the actual data as it's coming in. So we need to segregate the, as you were mentioning, development and test from actual customer data. So what is the format, a generic format that you're using, or is there a config file that you're using to create these simulations? Because one thing what we're trying to do is validate, are the MapReduce jobs, or all the data processing, is it working properly without using real customer data? And that's becoming a challenge.
Exactly. In fact, that's how we found a bug in Hive once upon a time. We had a customer with private data. They said Hive's broken. I talked about this in another talk this week. And they couldn't give us any data. And we had to emulate their data, some ungodly number of tables all joined by foreign keys and stuff.
Right.
This is a quick snippet of a configuration file for LogSynth. The format of it is JSON. And the overall structure is a list of variable definitions. And the variable definitions are specifications for distributions. And so here you can see the name of the variable is going to be X, the class is integer, and it's going to be a skewed integer with some unknown min and max.
Yeah, this looks very similar to what we're building, but
yeah.
So
well, steal, don't build.
No, that's so I will take a look at what you're working on.
And so you have as many of those as you like. Those can each generate JSON structures, and they can also generate JSON structures that are marked as flattened. That means that the components of that structure should be promoted to be top-level variables in the final result. It will format the output either as CSV, TSV, or JSON, or whatever you want to install. And it'll also output the data as expansions of a template.
Got it.
So that you can generate weird stuff like V cards.
Right, good.
So,
Thank you.
yeah, Steve.
Yes, so the main point of your talk is you made this assertion that when generating random data, the only thing that really, it's not the only thing, but the thing that, you made this claim that as long as the error rate and KPI matches the real data, then that's good enough. But your proof of this assertion, it really just seems like one example. I mean, do you have a more rigorous explanation for why that is the case, or beyond just?
You're absolutely correct that the one example here is n of 1.
Mm-hmm.
It is not a very persuasive proof in any mathematical sense. But if there are KPIs which all actually recognize the figures of merit that you really have for your system, then by definition, anything that replicates those is good enough.
Mm-hmm.
Now, the questions become, are the KPIs complete enough? Is there some subtle thing, some KPI you haven't added to your set yet, which is important? Well, this is a great way to discover it.
Mm-hmm.
And secondly, is it easy to generate correct KPI generating mechanisms? The second one is just an empirical thing. I find it pretty easy, but it's only an empirical thing on dozens of examples, not across great sweeping swaths of axiomatic mathematics.
Okay.
It's a pragmatic observation.
Thank you.
Well, thanks everybody. I'd love to work with you on LogSynth, generate more bogus data. Yeah.